Hello, everybody. Welcome. Thank you for coming. I'm going to try not to dance too much. My name's Dave. Hello. I work on the .NET team at Microsoft, and I'm going to tell you what's inside a .NET assembly. This is a little bit of a funny talk, I think, but I know what's in it. Kind of changes gears halfway, but we'll see. We'll get there. Hopefully it's you can keep up. So that's what's inside a .NET assembly. No, I'm just kidding. If this was the session before lunch, you would all be loving me right now. So this is ILSpy, and hopefully maybe you've seen this or a software like it, .peak or .NET Reflector or whatever's built into your IDE. And hopefully it's a little bit familiar. I'm not going to go into every detail because two reasons. Number one, I don't understand it. And number two, there's really good blog posts written by really smart people going into like what is in the DOS header and the COF header and what all of those things mean and what's a Windows PE file and all that sort of stuff. I don't care about that. I like .NET and C# because it's very high level and I don't really want to have to know about the low level. And in fact, I spent most of my career trying to avoid knowing most of the things I'm going to tell you today. But then I found them out as part of doing my job, which is annoying. But there was some really interesting things, so hopefully I will impart the interest onto you. The things we're going to talk about. So what's in a DLL? Well, there's metadata. Information about your DLL. This is the thing that makes .NET really cool. I will explain why later. Not unique, just cool. Specifically, metadata tables is what I'm going to be telling you about in the next 15 to 20 minutes. And then the other part of a DLL, obviously, is your code. Hopefully that one's not a surprise. Hopefully this next bit's not a surprise. It's not C# in the DLL. It's this wonderful thing called IL, which is another thing I never wanted to know anything about. And I've managed so far to be okay with that one. I don't really understand it. But we'll get back to this. So that's what's in a DLL. We're going to talk about metadata tables, though. What is inside a .NET DLL is a relational database. That is my political stump speech. That's my slogan I'm running on. It's a database. It has all the things a database has. See this token column? That's a primary key. That's how I want you to think about it. This table is called typedef. So just to, ILSpy shows the number at the start is the index of the table. It's table 2. This is defined in the spec for .NET, ECMA 335, all that stuff. It's table number 2. It's called the typedef table, though. And it has 2 records. That's why there's another 2. Gets a bit confusing with ILSpy, so ignore that. It's a typedef table. This is the list of types defined in this DLL. This is a database table. So it has a primary key, right, a token. We can see there RID, that stands for row ID. So row 2 is token 02000002, row 2. And its name is program. That's the program class, right? Hopefully not a surprise, there's a program class. This table also has a foreign key. There's a method list. And that says 060001. And if we look over here in the method table, there's a primary key, and we look up 060001, and what's it called? It's called main. Now, it's called main with little dollar signs and funny squiggles. That's because this is from top-level code. Hopefully that's not scary, but that's what the C# compiler produces. I'll get back to that. So it has primary keys, it has foreign keys. It's a database. What this is a database describing your DLL, and it describes it in a lot of detail. So, for example, apparently not. Apparently first we're going to talk about metadata. I've forgotten who did these slides. Okay, so primary keys. We'll talk about primary keys first. A metadata token is kind of the key to all of this, right? The method list, the data in there, that's a token, so that's an ID, right? The token, obviously, the primary key, that's an ID. These IDs are everywhere. And because ECMA 335 is, written by people who write specs, not me, and by really smart people, they see something like an integer, and we might think, oh, that's a number. These people, no, they see an integer, and they think, I can cram many numbers in there. So a metadata token is 4 bytes. The first byte tells you the table that the ID is for. Now, this is where the relational database idea kind of starts to break down because this is super weird and not something you do in a database. But go with me, it works. And then the last 3 bytes are the row number. And that's obviously in hex, so you will see letters later in the talk. They're just numbers. And this is used to really cool effect. So if we go back to this method list, right? Now, the column name here says method list. So this one's like, it's not a great example. There's better examples later. But this field points to another row in another table. And conveniently, it tells us what table it's pointing to, because the first byte of this token. So it says, my method list is in 06. Well, it turns out all methods are in 06, so that one's, bad example, as I said. But it works the same for fields, right? I don't know off the top of my head what the field table is, but I'm pretty sure it's number 4, because that's number 4. You'll notice that's all zeros afterwards. That means there aren't any fields. I'll explain that as well. Base type. Here is a good example. Finally, we get there. The base type, and if you can actually see under the arrow there, the first row there, the base type is 02. The second row, the base type starts with 01. So these two things, and ignore module, I don't actually think anyone uses modules anymore. It's a little bit of an ancient thing from .NET, but each of these two rows has a base type, but their base types come from different tables. And all of that information is encoded in the ID. So the base type 010000D, if we look that up, 01, it turns out, is the type ref table. So type def is types defined in your DLL. Type ref is types referenced by your DLL. This definition and reference concept comes up a lot. And so the type ref table, if we look up row D, its name is object. And, well, yeah, all types in .NET inherit from object. And so when I say that the metadata describes what's in your DLL in detail, I mean it, right? This is detail. You don't normally specify that program inherits from object, right? It's implicit in C#. But this isn't C#, this is .NET. And .NET can support any language, and maybe it supports languages that do require you to specify it, but even when it doesn't, .NET requires that base type. And so you start to see these metadata tokens everywhere, and particularly the first byte there, right? ILSpy, as I said, it shows you there. You see it everywhere. And it's really key to understanding these things, because what sort of at first glance looks like number soup turns out to be, it's just useful information. So if we go back to our IL, of course, so ILSpy is really nice. All these programs are nice. Instead of showing you IL, they usually show you C#. You can say, no, show me the IL. Turns out you can't stop them being nice. They're still being nice. So if we look at line 12, it says call void blah, 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 console write line. That's not what's in your DLL, obviously, right? What's in your DLL is there's an IL opcode, right? So there's however many bytes of data in that call opcode. And then there is 4 bytes, which is the token to call. And you can see it here on the end. It's 0A, 00C. So what table does that come from? Well, we know because 0A is the member ref table, right? So this is a method that we're referencing, not one we've defined. And so this concept of baking in the table into the ID means we don't need an IL opcode for call a method in another DLL, or call a method in this DLL, or call a property getter or a property setter or a fielder or whatever. We just say call something, and the something fully describes what it is. Fully describes. So it's the member ref table. We look in the member ref table, we go down to row C, right, which is 12, and it's called write line. Great. It has a parent, which is 01 row E, so we go look up the type ref table. Row E is the console class, right? This is where the code comes from. We go further, we look up the resolution scope. That's the assembly it comes from. I assume there's some other resolution scope that can be used in .NET. I doubt you'll ever see one, but there is. But that's in row 23, table 23, sorry. Row 2, we look that up, it says system.console. So when I say that this encodes all of the information about your DLL, it encodes all of the information about your DLL. Your console.writeLine, which comes from system.console because maybe you've got a using in C# or a global using in the project or whatever, none of that stuff actually matters to .NET, right? There's no using directives in .NET. There's no global usings in .NET. There is just this data. So the compiler goes and works out, the console class, that comes from here. But it has to encode in this every single bit of information, right up to, and this is where it stops here at the assembly level. And so the assembly name, which is actually the name and the version, and the public key token, I think, sometimes, for strong names. Anyway, that assembly level, that is the the extent that every bit of information has to go to in this metadata table. So this database fully encodes everything your code is trying to do. So why does that make .NET cool? Well, I can compile a DLL in .NET on .NET Framework or .NET Core, and I can reference .NET Standard, whatever that is, and I can run it on my phone or my PC or whatever, and that DLL can be moved around everywhere. And the reason it can be moved around is because this data exists. The compiler's job is to describe what's in the code up to the level of assembly names. It is the runtime's job to then go and work out where is that code, right? Where is the write line method so I can actually write it? This doesn't have like memory addresses of where the write line method is in the system.console.dll, right? Because if you're on .NET Framework, it's in mscorelib.dll, and if you're in .NET Core, then it's system.private.corelib.dll, and if you're in WASM, it's God knows what, right? But all of this stuff is, by encoding it in the database, the runtime takes care of actually doing the execution. So this is what makes .NET portable. This is what makes us be able to take our DLLs and upgrade them relatively easily, right? This is why I don't need to recompile my whole app when one thing changes, because all of this stuff is just described in the database. So that's why it's cool. I wish I was clever enough to tell myself what the next slide was, but I think I know, so I'm going to keep talking. Okay, that's the database. Fine. That's what's inside .NET. Okay, fine. That's not interesting. The interesting bit is what's not here. And this is where we have to look past ILSpy, because ILSpy is very nice. In fact, every tool that looks at these DLLs is very nice. You have to just kind of trust me, but, we'll see. .NET DLLs are produced a lot, right? Every time you compile, you produce a DLL. The compiler writes this database out. And essentially what happens, if you can think sort of fourth dimensionally, right? This database doesn't exist at all. You hit build, the compiler writes out this database 1 byte at a time, then it writes out your IL. That's written to disk, and it never changes, ever. Right? A DLL is not updatable. So this database is not updatable. The other thing about DLLs, or the same thing again, because they're written a lot, we kind of want them to be relatively small, or as small as possible, right? We don't want to force you, by us on the .NET team writing this crappy system, to have these huge DLLs everywhere. So efficiency is super important. And if you take this concept of we want to be really efficient, and we know this database is written once and never updated, and we know that there is a full spec for what should be in this database, we can do some little tricks. And so one of those tricks is baking in 4 bytes, 2 numbers into 4 bytes. But the other trick, and that I think is the most interesting, is all of these primary keys in these tables, they don't exist in the file at all. They are not in the database. In fact, if we go back to, that'll do. The field list there, how I said that was 0. That means that there are no fields for this table. The way I know that is because it is a rule in the spec that every single table, the data always starts at row 1, and it always increases one at a time, no gaps, no skipping numbers, right? No jumping around. Every table also has a defined order of data as per the spec. So all methods are written in the method table there, are written in the order of their types. Now the type is not in the method table, so you just have to know that. But so there's a spec for writing it, the compiler writes it, and then everything that reads it in according to the spec. So we don't need these primary keys because, of course, if I'm reading the type def table, which I know I'm doing because I'm writing a reader, and I'm reading row 1, which I know I'm doing because I'm writing the reader, then I know what the metadata token is for row 1, right? So there's no primary key. So there's no metadata tokens, right? The method list is written because something has to tell it where the methods start. We'll see later, some tools show method list as an actual list, or like as a start and end, because it's called method list. ILSpy shows it as one number. It only writes, the only thing that's written to the file is the first method in a table. We don't need to write where the last method in a table is, because we know where it is, because we just read in the next row of the type def table. And so therefore, whatever method number the second type in the table starts at, well, the previous one must end at that -1, right? So there's these really standard rules, and they're all about efficiency. But, yes, I was right. But how does hot reload work? You don't ask, because why would you? Well, I'll tell you. It's all well and good to stand up here and talk about tokens and numbers. That's kind of boring. It's good to know, but where this comes out in the wash, I think hot reload is a great worked example for this. So I'm going to talk about that. The other reason is, this is why I had to learn about this stuff, so you can share in my misery. Here is your conceptual model for how hot reload works. It is a 3-step process where you're running some code, you decide to change it, you want to compile it, and then the runtime has to deal with it. Obviously, this is wrong. This is the actual process, and the reasons, no, it's not wrong. The actual process is slightly more detailed, and it's again back to efficiency, right? If every time you did a hot reload, we recompiled your whole solution, and then we send these multiple megabyte DLLs to the runtime and said, here, have fun. That wouldn't be very nice. You wouldn't enjoy the feature, and please don't comment if you already don't enjoy the feature. That's not what I'm talking about. Anyway, so what happens in real life? So you're running your code, fine, you edit your code. Step 1, we have to work out what has changed, right? We want to be efficient, so we only want to compile what has changed. Roslyn does this work inside the tooling layer, so the IDE works out what has changed. And then we tell the compiler, please compile this project, but we give it a list of what has changed. So we say, hey, compile this project, fine, but really, this is the only thing that's changed. And so the compiler creates what's called a delta compilation, right? The compilation is the difference between the original thing you wrote, which is called the baseline, and then where we are now. We send that delta to the runtime, so we're giving a smaller little packet to the compiler to compile. The compiler is going to produce a smaller little packet of bits, and then we send that small packet of bits to the runtime, and it does its work. And it's got less work to do, because it doesn't need to work out what's changed. We've already told it. And each time through this loop is called a generation. Generation 1, generation 2, you'll see that in a minute. And the other thing that's sort of key here is we have to talk in terms of .NET, not in terms of C# or VB.NET. So let's do a worked example. Here is some code, 3 methods, pretty boring. Here is our baseline method def table, right? We have tokens 3, 4, and 5 for methods A, B, and C. You can imagine 1 and 2 is probably like a constructor or something else, static constructor, I don't know. Doesn't matter. So we have our table, 2 from 3 fried. We're going to make an update. We make an update to method B, we make an update to the string. So working out what has changed, well, it turns out Roslyn's actually really good at that because there's a syntax tree produced and we have a before and an after and we go, what's the difference? And easy, it's a string. But in the metadata tables, in that database, there is no table for string, right? There is no table for line of code in method B or any other method. So what we have to do is we have to look back up the code to find what is the smallest unit of .NET that has changed. And in this case, that's the method B. And so we have our to-do list, which we give to the compiler, and we say, hello, please produce a compilation, only compile example.b. And the compiler simply goes through every single class in your project, and it says, oh, class foo, is that on my list? No. Right, next. Class example, is that on my list? Yes, okay. I'll keep looking. Okay, found method A, not on my list, don't care. Method B, great, it's on there, I will compile it, I will write out method B. And so it writes out a delta compilation with a method def table for B, right? And tokens don't exist in the file, so of course it doesn't write a token. That's not its job. Then we're going to make an update to A, and we'll make an update to B as well. So this is now generation 2. We produce a to-do list of 2 things. We tell the compiler to compile our delta, and it produces these 2 rows. Everybody with me? Everyone happy? Good, because I'm talking super fast. So, can anyone predict a problem? I see nods. Do you want to shout?
When you add an extra function in there, it's going to change the length of that table, and all the subsequent tables are going to be buggered.
That's a very astute observation, but there's actually an even simpler one. As these deltas are being read in, the tokens are all wrong. Method B on this one slide is ID 4, 1, and 2. Right? So our rule that gets us really efficient DLLs, because we know we're never going to update these things, Well, it kind of poses a problem when we want to update them, right? Shock horror. So how do we solve that? I was going to do the demo now, but I'll wait. So how do we solve that? Okay, the way we solve that is with more metadata. Yay. So this is back to metadata, right? And we have these tables at the top. I've expanded the debug metadata in this bit of the screenshot. So this is what's in the PDB file. PDB stands for Program Database. It's a database. Again, with the eye to efficiency, and we don't want these files to be big, everything that is necessary to run your code goes in the DLL, and everything else goes in the PDB. Now, these days, PDBs are pretty small. Portable PDBs are really quite small compared to native PDBs, and you can embed the PDBs in the DLL, and I thoroughly recommend you do because it's really cool if you're ever debugging your code. So this separation, I mean, it's still there, it's fine, and it's still important. PDBs can get huge, depending on your project. But so this is where we just shove all of the other information we might need. Hot reload is obviously a debugging scenario. It doesn't have to be debugged. That term's a bit blurry now, but it's not needed in production. So it goes in the PDB file. The PDB file just has extra information, just more, right? So document stores literally which file did each of these methods or types come from. That's good for like go to definition or for showing you fancy errors and that sort of thing. Method debug information is just a bunch of random stuff to help the debugger debug methods. Local scope is to help the debugger show you like local variables and things, right? The way that it gets the name of the variable to show in the debugger, that comes from the PDB file because, of course, the name of your variable is not important at runtime, so it's not in your DLL. And there's more stuff. There's lots of tables. These days, we seem to just shove everything in custom debug information because it's like we put a bucket here just in case, and now we just like, we'll just put everything in the bucket. So yeah, I think, look, I drew lines. But there's more tables that aren't shown here. So there's this option in ILSpy that says hide empty metadata. And so you turn that on and you get a bunch more tables, right? You get some async state machine stuff. So state machine method is for async methods and yield iterators. And we have to store in there where the states are so that if you add a new one in, we have to shovel everything around. And it's really lots of fun. But there's two more tables that aren't shown here. And they're not shown because they never exist in any DLL because they're only used by hot reload, which never exists on disk because we can't update the DLLs, right? They're called ENC log and they're ENC map. And I love them because if you load up ECMA 335 and you search for the term ENC log, you find exactly one result and it says, oh yeah, there's this table, we'll use it, don't worry about it. It's great. And so, if these people don't document their code, I don't have to, that's my problem. But they exist, trust me, and there's one tool I know of that will show them, which is called MDV. This is the only official tool that actually looks at DLLs now, because ILDASM's kind of gone away. This was the person who wrote MDV, when he was teaching me about all this, he said, this is the only tool you ever need to look at DLL files. Oh, that's good, that sounds exciting. And then I used it, and I'm like, what does all this mean? He's like, oh yeah, it's written for people who've read ECMA 335. I haven't read it. Anyway, it's not that bad. Let's do a demo. Okay, bear with me while I get my fonts and everything right so that all you fine people can see. Oh, God. Oh, no. Hang on. I'm starting that again. I zoomed too far, and then the program crashed. How do I zoom without... Okay, is that cool? Okay, so this is our very simple program that writes out three things. It's not so simple anymore because it now runs in a tight loop, right? Outputs the clock at the top so you can prove I'm not lying. And all it does is it calls method A, B, and C, makes sure it doesn't crash so it catches exceptions. You can see that here, just got to catch. And runs again, that's all. And so we're just going to use it to, I'll do some hot reloads. So first one, we updated method B. I press the hot reload button. It updated, it worked. And then we do method 2, it updated, oh, sorry, I'll click update. Cool, they both updated. Great, we're done with the program. So, I just did what was on the slide before. Obviously, you didn't see what happened behind the scenes, so I have to show you now. So when I said that these things are never written to disk, I was lying. I have, actually, I'll do this from the command line. I have on my machine a very secret, it's not at all secret, environment variable set, which I can go to NC output, and I can go to, hang on, oh yeah, 2, okay. And then I can go to here. Okay, so in here, because I have this secret environment variable set, Roslyn is dumping everything it knows when it does a hot reload. So what this is we have our baseline DLL and PDB for when I ran the app. We have the code that I changed, old and new, for generation 1, generation 2. And we have the IL, the metadata, and the PDB differences, so the deltas, for generation 1 and generation 2. This is what Roslyn produces, right? Normally just as a stream of bytes that it sends to the runtime, but this is what the compiler produces. They're not, like, it's not a DLL, so I kind of wasn't lying, I kind of was. And if we run MDV, and I'm just going to output that to here, MDV will recognise this file structure and it will do its work. And if I open this up and then zoom again, oop, too far. Okay. So this is everything MDV knows about the DLL and each generation. And so what we're going to see, much like ILSpy, it just dumps out all the tables, but much like ILSpy, if we go here is our methods A, B, and C. We are row A, C, and E. That's odd, but okay. I don't know. It did what it wanted. Oh, sorry, no, that's not the... Sorry, that's not the... I'm seeing letters and assuming they're actual numbers. They're not. Ignore that. Right, row 4, 5, and 6, great. And you can see in the type ref table here, so see this, whoops, see this methods, right? MDV doesn't call it method list, it calls it methods, right? Well, the name's not in the DLL file, so really it can call it what it wants. It includes this end thing, like I was talking about before. That's not really there. It's just being nice. Everything here is very nice. But so it dumps that out, 4, 5, and 6. If we scroll down, eventually we've got lots of data, so much. It's like we just write so much stuff. It's crazy. Look at all this stuff. This is like, well, it's not the simplest program in the world because it does have all that looping stuff. One moment, please. Okay. This is method A. Yay. So this is the IL, right? And we can see this is method A, and it's for token 0604. Here's 5, here's 6, right? So the IL is written out sort of outside of the database. Cool. Here's generation 1. So we've applied our hot reload. We've told the compiler, please compile method B, and the compiler has done exactly that. Here is the one method in this ECMA 335 compliant byte stream. And therefore, it's row 1, because it can't be anything else. Has to start at 1, can't skip any numbers, right? So the compiler can't possibly say, oh, this is row 5, just, trust me. It's not allowed, right? Presumably the thing reading this would then crash. So what we need to do is we need to say, okay, so for generation 1, what you are reading as row 1 is actually row 5. And the way we do that is, ta-da, the ENC log table, previously ever seen before. We'll go with ENC map. No, we can go with ENC log. For the purpose of this update, they're actually both the same. Some updates it needs both and they store slightly different data, but essentially, you can see here in this log, this says token 5. Now, that's not a lot of information. It's one number. But, we're still in this mindset of let's write as little data as possible. The unwritten thing here is every table has a defined order. That's true for ENC log as well. So ENC log is written in order of the type of thing that it's logging. So all assemblies, then all members, then all types, then all methods. Therefore, when we get up to a method, which we know because it's 06, we know that we're reading not row 1, but the first log entry for a method. Therefore, this must be method 1. The data says method 5. Oh, method 1 is method 5. Okay. So this is kind of update methods where ID equals 5, select from where ID equals 1. And because the method table, if we go up here, it doesn't have, like the key's not there, right? All of the data here is just pure data. And so every single field can just be blitted straight over the the in-memory representation of this. And so what happens is the runtime reads this, this log and this map, which tells it what to do. Like you can see here, the map is a slightly different order, but it's the same thing, right? It's the first method in the map is row 5. This actually tells it it's an update. There's also, you can update types by adding methods. And so to like your point earlier, the map comes in more handy there where it's like, oh, I'm adding a method, but it's to this type, which means that what's row 1, well, it doesn't actually have an ID in the current DLL because I'm adding it, but by telling you the type, you can see where it would fit. So a bit more information there. But the runtime will read this, and it will do the mapping and it performing, and essentially it's updating its in-memory representation for this metadata, which is what you're querying when you use reflection. So when you use reflection, you say, give me the types in this assembly, it's this data you're looking at. And then you say, give me the methods, gets to this data. And that's all cached so that you don't have to, when you call it again, it's got the data ready. So when you do a hot reload, the runtime also clears its cache, and then next time, and then we go down, here's our string, here's method B, right, the only method output. Now the easy part, we get off a little bit easy here because IL, as I said, it's stored differently. So this one just says, yeah, this is the IL for method 5. Doesn't matter that method 5 isn't in this specific DLL, no one cares, it exists. Here's generation 2, same thing, right? Method A is now 1, B is 2. We now have 2 method defs in our log, 4 and 5. They're in the right order. We know where they are. And that's how hot reload works. And so that's how we can update our DLL without updating our DLL. And so because of the efficiencies here of not specifying tokens, we kind of have this extra hard step, right, where we have to write this log out. But we also kind of get some shortcuts because, yeah, we can just output the IL like this. We can just blot all of this data and just go, yep, there it is, new method, done. Don't worry about it. That's the demo. That's the slides. So, what does this information actually, why is this useful? Well, I don't know, but hopefully I will tell you. So, have you ever been frustrated at hot reload? He asks, not wanting an answer. For example, when new C# features come out, hot reel, edit and continue, doesn't support them from day one usually. Why? Well, these are leading questions. When records came out, they weren't supporting edit and continue. What happens with the sort of work processes of the Roslyn team is the compiler team write the feature, obviously. They do all the compiler work, and they are responsible for basic IDE functionality for the new feature. So for example, with records, the compiler team would be the people who are responsible for making sure the word record goes blue. And that's usually just adding a new thing to a list somewhere, right? And in the same way, they're responsible for making edit and continue work. What that means is they make it so that when edit and continue sees a record, it goes, I don't know what to do, but it doesn't crash. That's the extent of their work. And then the IDE team come in and go, all right, we'll make this work. So when I said we come up with a list of changes, we have to come up with a list of changes in terms of .NET, not C#, right? Records don't exist in .NET. They exist in C#. But they have a meaning in .NET. And so we have to write the code that translates that meaning, right? So when you add a property to a record, well, when you add a property to a class, you're adding a property. Okay, easy. When you add a property to a record, you're adding a property. But that would also mean you have to update the print members method because it outputs every property. You would have to update the constructor because the constructor will take in every property. You have to update the equals method and the get hashcode method because they look at it, right? And so we have to then write the code that says, oh, property changed, it's in a method. Actually, compiler, I want you to do these 6 things. Not just the one thing the user changed, but the 6 things that are affected by this, right? And so thinking about things in terms of .NET like that for these new language constructs, so if you're up on the news, and I don't want to spoil Philip's talk later, but extensions are the big thing in C# 13, right? And a lot of people, some people don't like the new syntax, fine, it's been a story. But there's one part of extensions that trips everyone up as like, oh, that's weird, why does it do that? And it's extension properties, and when you have multiple extension properties that have the same name in the same scope, right, that's ambiguous. You have to tell the compiler which one you want to call. When you have extension methods, the way you do this is you just call it like a regular static method, not an extension method, it's like fine. But you can't do that with properties. And so the way you do that in extensions in C# 13, pending future possible changes, is you write get underscore property name as a method, right? Which is kind of what properties are compiled to anyway. But what's funny is some people see that and they go, oh, that's really ugly syntax, why did you choose that? And I'm like, well, they didn't choose it. That's how you have to write it in a metadata, right? How else would you possibly do it? It's a method. It looks like a property in C#, but properties in .NET assemblies don't have code. They're like, helper definitions, but there's a get method. So sometimes it's a matter of that translation between C# and .NET. And so sometimes you do run into this in your life, and so like having that understanding is cool. Let's see, what else? Attributes. You didn't used to be able to update attributes on things. Now you can. As a completely off topic, but this list of questions is almost a list of things that I actually worked on, which is why I know about them. Except I didn't do async await or generic types. But anyway, so you couldn't update the attributes, right? And this one is about knowing how these foreign keys work. The foreign key I showed you is actually kind of a backwards foreign key. You don't normally in a database point to the other record. You would have the other record point back. So you would have, if you were designing a database, you would have a method table, and each row would point to the table it is from. Okay? That's how we normally do, normalized databases. But of course, that just stores extra data, so we don't do that in .NET. We have to make life hard. The attribute table actually does work that way, because attributes can be on almost anything. It can be on a property, a method, blah, blah, blah. So it turns out it's actually really quite convenient to say, here's an attribute, it's for this thing. And this thing, because it's a metadata token, because it tells you what table it's from, that's all you need to know. I know whether this is now an assembly attribute or a method attribute or a property attribute, etc. But of course, updating that was hard because the attribute table has to appear in a specific order, and that order is the order of the types that they come from. And so if you add a new attribute to a method, it pushes down all the rest of the attributes on other methods, and maybe it pushes down attributes on whatever table comes next. And so the compiler couldn't output that table as part of a delta in a way that the runtime knew how to update it. For that one, we cheated, and we just always output all attributes every time you compile, because sometimes getting the runtime to do some work is, they have other priorities. Await and yield return, the state machine scope table I mentioned before, that didn't store enough information for you to be able to update awaits and yields. You could edit the code between awaits, but you couldn't add new ones. And you could edit the code before the first one, I think. Anyway, because the numbers weren't affected. Each time you do an await, that's a new entry in a state machine. So we added more data to the state machine table to track your state machines, and now we can. So sometimes it's about educating the compiler to write more metadata. The other thing about state machines, not strictly related to hot reload, but sometimes in, like if you see a memory dump, or sometimes in exceptions, depending on what symbols you have, there's state numbers for each point in an async method, and those numbers directly translate to if the state says 3, then you are at the third await in that method. And that could be super useful for debugging if you've here's a stack trace from a method, I have no idea what it's up to. So actually, it's right there. So again, no metadata. Generic types is a great one because this was impossible for years, and on the Roslyn team we would talk about it and we're just this is never going to happen. It's just too hard. And then I don't know what happened, but someone at the runtime said, oh, we can do that, and they did. And now it works. There was almost, in fact, I don't think there were any changes to Roslyn to allow this, except for changing the tests that verified it didn't work had to change because now it does. But this is where the runtime has its sort of in-memory database, and it has to update that. So you update a generic type, right? You add a method to a type, it has to update this representation, fine. But of course, a generic type, well, there's one instance for ints and one for strings and one for whatever, and it's got to do all that work. They just wrote that code. And then the final one is Blazor WASM, which I actually don't know the current state of this because I haven't been involved in a while, but it's a lot better than it was when I first worked there. Blazor WASM uses Mono, the Mono runtime, and there's lots of code sharing, but specifically the edit and continue code Was not shared. I don't think it is now, but I don't know. And Mono only supported updating method bodies. And it turns out that if you can't add a method, there's really not a lot you can do in .NET. Well, sorry, there's not a lot you can do in C# because the C# compiler really loves synthesizing methods for you. Every lambda you've ever written is a method, every property is 2 methods, every event is 3 methods if you're in VB.NET. It's great. And so they added making new methods, and that unlocked a bunch, but then they've kept working. The edit and continue code in the runtime for this is all in C, and it's horrible. Well, all C is horrible. That's my opinion. All right, back to demos. This is the whole reason that you're here, is because I love doing this demo. The whole reason I'm here at this conference. So I'm going to run this app again. I think, yes, I did hit the thing. I'm going to zoom again. Oh, God. Okay. We're cool? We're on top? We're running? Okay, let me just prove it works. And we'll do a hot reload. Yay. Okay. Welcome to enterprise coding. This is not how you do it. This is silly. Why would you hard code a string? I want a method. I want a method called public static string get message. And we're going to return, yes, that'll do, type thing. Come on, Copilot. No. There we go. Sometimes you just got to like remind it. It's like, sorry, I typoed. I didn't mean to disrupt you. Okay, so I'm going to make this call get message. Cool. Hot reload. Cool. So this now says hello from get message. Hopefully you can see my cursor. Yep. Now on the right here, I didn't explain this before. You probably worked it out. This is just using reflection to query what methods are in this DLL. And so you can see down the end here, we have now got a get message method. It returns a string, takes no parameters. Okay, fine. Of course, if I update this to say get message, well, this is silly because they're going to say the same thing. What I actually want to do is I want to tell it what method I'm coming from. So I'm going to come down here and I'm going to add a thing here, and I'm going to just do that because I'm old, so string concatenation is my favourite thing ever. I'm going to hot reload. Oh, that's a zoom problem. Oh no. Is it still running? No, this is... No, it's my console.go to column 50 and then write is failing because I've zoomed in too much. Demo fail. Okay, we're starting again. Well, actually we're not. We just do that. Yeah, okay. Sorry, running again. I'll stop there. Hopefully you can still read that. Hopefully that works. All right, let's just redo this. Okay, so I'm going to hot reload. Now, someone correctly called out that I didn't update method A. You are absolutely correct. Hot reload, I didn't care. Why? Anyone know? Wasn't on the to-do list. I didn't change method A, so the compiler never looked at method A, so it didn't compile it. Therefore, it didn't see a compile error. Therefore, it happily produced a DLL. Now, the IDE is compiling all of my code, and so it's got a squiggle and says, hey, idiot. So what happens there is hot reload has worked. Now, your app may not, right? I happen to write all of my code with try catches around every line just in case. But no one does that. So this app is still running, but as you can see, like it stopped working after calling method A pretty clearly. What's cool here is we now have 2 get message methods. One takes 0 parameters, one takes 1. But what I actually did was I added a parameter. So in terms of C#, I added a parameter. What I did in terms of .NET is I added a method, and then I removed another method. The runtime does not support removing methods. None of them do. I created an issue for it, they haven't done it yet. And so what we do in Roslyn is we cheat. And we say, okay, well, we know that they can't delete a method, but they can update a method. And so this get message here, which has 0 parameters, and you'll have to trust me for this, the contents of that method is 1 line of code that says throw new missing method exception. And that's the exception that A is hitting. So at runtime, this method still exists because we didn't delete it. A is still calling it because it exists, but it happens to throw an exception. This app catches the exception, all is fine. Method B is calling the other method, and that's all fine too. So I can update this, I can hot reload, the program is resurrected from the dead, and all is good. Now, speaking of resurrecting from the dead, if I do this and I'll reload, nothing visibly has changed here, well, except the messages. What's actually happened there is I've now deleted the method that has the one string parameter, and I've added a new method which has no parameters. And so we've pretend deleted the one parameter method. So that one now says throw missing method exception, hard to say. The other one has been updated with the real code. And so in reflection, it looks like two methods. In C#, it's just one. And this gets really cool when you do things like, oops. Oh, God. Hang on. There you go. Public static string prop. So we do that, and we hot reload, and it crashes. I can't believe it. Anyway, what would have happened there was it would have said, oh, I've added a get myprop and a set myprop method. And then you change the return type of myprop to an int, and it says, oh, well, I better add two more methods, and then these two I'll throw missing method exception. And then if you change it again, it adds another one, and your number of methods quickly expands. But that's okay, because these things are never written to disk. And so that's the fun, of committing crimes with hot reload. Because we produce a to-do list for the compiler, if we just say to the compiler, hey, this method hasn't changed, or rather we don't say it has changed, it will just skip over it. So that's fun. Now the real actually useful lesson from that is sometimes you have to modify a method to get hot reload to do what you want to do because it doesn't know about it otherwise. If I change a method, let's say I change this, what's a good example? Well, if I change the return type of this, right, from string to int, in console.writeline it's not going to matter, but strictly speaking, what's now happening is a different overload of the writeline method is being selected and being called. But unless I actually touch method A, it won't be updated, and so the old overload will still be called. And that could be surprising to you, and so something to be aware of. The other thing with hot reload that this demonstrates a little bit, hot reload is responsible for updating the code. It is not responsible for making sure it runs. And what I mean by that, this code exists in this tight loop, this infinite loop here, in fact. If I had changed any method, if I just got rid of this and done hot reload, nothing would have updated. Because even though this main method got updated, got seen by the IDE, we compiled it to the DLL, the runtime updated its representation of it and the IL of it, but it's running. It's still running. It's not going to stop. The next time it stops and tries to run again, it'll be using the new code. But if it's already running, it's still running. Now, edit and continue is actually a bit smarter about this. It's much more complicated, but edit and continue can do this, which is the big difference between edit and continue and hot reload. But as far as hot reload goes, it doesn't run your code. That's up to you as a developer, if you want to, make sure you're running your code. That's why things like top-level programs, like top-level statements, are very difficult for hot reload. Like if you're using minimal APIs in ASP.NET and you change a route on one of your things, hot reload doesn't care about that because that's the main method, right? It's not going to get restarted unless you restart your app. There's ways and means, though. There's an attribute you can put, and you can actually do this in your code. You can put on a metadata update attribute, and basically the runtime, you're saying, hey, runtime, whenever you apply hot reload, call this method. And it tells you which types are updated, and you can actually do this yourself. So I have a little game that I wrote, and I cache a lot of the bitmaps, right, for performance. And I have one of these update handlers, and all it does is, oh, hot reload was performed, let me just clear the cache. Because just in case I'm changing a drawing routine, I want to be able to see the results. So, that's it. That's my talk. Thank you for coming to my hot reload talk. It was masquerading as a What's Inside .NET assembly. You're all part of a very long-term A/B experiment as to what talk title this should have. There'll be a survey, no, there won't. Does anyone have any questions? Yes, JT.
Can you explain the difference between hot reload and .NET Watch run in the command line?
Sure, nothing. So, .NET Watch is another entry point into hot reload. It is currently being rewritten by the person who told me that MDV was for people who read ECMA 335. Well, a lot of that has already happened in .NET 9, but it's ongoing. It's being rewritten to share a lot more code with Roslyn, so it will work the same as in the IDE. But essentially it does the same thing. It monitors your files. It knows what has changed. It used to be a little less clever about what has changed because Roslyn in the IDE has the benefit of all of your code is in memory, like as a syntax tree anyway. .NET Watch, that wasn't true. So it tended to do sort of broader updates, but that doesn't really matter. But it had the same basic capabilities. The big thing with .NET Watch, and this is also coming to the regular IDE tooling as well, is it's this interesting thing you run into as a developer sometimes where you write the code and it fails for some reason in production. And you think, oh, God. In fact, I saw it today during Steve's keynote. I don't know whether anyone noticed. There was a little grey bar at the top of Visual Studio. Did you notice? Yeah, that's my code that caused that. That's not a good thing. Right, that's me. I own the Razor editor in VS and VS Code, and that little grey bar says one of our internal things has crashed. Now, it didn't matter for his demo, and everything kept working, which is good. That's also our code, of course. But it's like, you notice that thing of like, oh, God. And I'm sitting there thinking, everything I've done up until this point in my life has been a complete failure. And Steve's up there happily demoing, and everything works, and you're all watching and going, yeah, this is a really good talk. Right? So you get to that point. The funny thing about .NET Watch is .NET Watch essentially works by brute force. And when it can't do a hot reload, it just restarts your app. Visual Studio does not do that because that seems like a really bad idea. Like, why would you want to just restart your app? Turns out everyone just loves it because they think the amount of people who say, oh, hot reload works so much better in .NET Watch than VS. It's like, no, it doesn't. It's exactly the same. But when it doesn't work in .NET Watch, it just brute forces its way through. It's like when you first do your lift and shift to Azure and your IIS app pool is crashing every 3 seconds, but who cares because the website's up, right? Azure just restarts and stuff. But yeah, so there's not really a difference, and there's less and less difference technically now and going forward. But it's like producing all these source packages out of Roslyn to share the code, and there's like it's all fun. But yeah, it's the same. Each specific feature is the same feature set. It is using Roslyn code. It is doing full hot reload. Everything else is shared. The experience is very different. Essentially, we need more emojis in VS, is what I'm saying. Any other questions? Brand?
Hot reload versus edit and continue.
So the biggest difference about edit and continue versus hot reload is just how much the debugger is involved and how much information is exchanged. So hot reload, it relies on the debugger to do a bunch of work of like ferrying data around. So like when I say we send the Delta compilations to the runtime, well, we actually tell the debugger, hey, this has been updated, and the debugger tells the runtime, right? Because it's got to happen in your process, and the compiler's not in your process and all those things. The biggest difference with edit and continue conceptually is the APIs to the debugger are much more detailed and they're much more fine-grained. So every time you step in the IDE, the debugger is saying, hey, what has changed within this span of this file? Because the debugger tracks the active statements using information in the PDB, and then it sends that back to Roslyn and it says, hey, within this active statement, or like this was the active statement, now it's here, what are you reloading? What do we need to do? And so it can do much more precise updates. And then the debugger has different hooks in where it can modify the contents of a method, whereas hot reload is just V1, V2, V3, moving forward over time. So yeah, what's funny is that edit and continue existed first, and it's by far the hardest one. And so as far as hot reload goes for like the Roslyn side of things, it just kind of all worked. It was like, it's actually easier. Yeah. All done? All finished? Okay, thank you very much. That's my talk. Thanks for coming.